In this video, we're going to take a look at how to make memory elements from logic gates. These memory elements are called latches, and then how to take latches and combine them to make flip-flops. Here's the circuit of a simple memory element that is made from two inverters. Okay, so we have an inverter, let's call it 1, and an inverter 2. And if the output of inverter 1 happens to be a 1, then that 1 gets fed back through inverter 2 and creates a 0 here. And that 0, when it goes through inverter 1, will create a 1 in turn at the output, so we can store a bit of 1 in this element. And similarly, if the output is at 0, then that 0 goes back through that lower inverter, creates a 1 here, and that 1 goes back through the upper inverter, and that creates a 0 here. So it's a feedback circuit, and it stores a bit of 0. The interesting question is, how can we change the value that is being stored in this circuit from 0 to 1 or from 1 to 0? The key idea that is needed to make the value of the variable that is being stored in the circuit changeable is to replace the inverters by NAND gates. Okay, so we have two NAND gates in here in the same configuration as we had the inverters before. Now we can go ahead and we can take this input here, for example, and go from 1 briefly to 0 and then back to 1 again. So the 0 at the input here will force the output of the NAND gate to a 1. And so the output is going to be 1. And the 1 is being fed back through the second NAND gate together with the 1 from the input of that second NAND gate. And that will make a 0 at the output of that NAND gate. And so now once we have a 0 here, then it doesn't matter anymore what this original input is. It will create a 1 at the output, and so we have a 0, actually a 1 stored here. And similarly, we can store a 0 by taking the lower input, setting it briefly to 0, so that will force a 1 at the output here together with the 1 up here. That will create a 0 at the output of the upper NAND gate. And that 0 then goes to the input of the lower NAND gate and keeps the output of that NAND gate at 1. And so we have stored a 0 in this circuit. So we have now the ability to actually change the value that's being stored in this feedback circuit. We can redraw this circuit in this form that is shown down here. That is called an SR latch, a set-reset latch. And the S in here stands for set, and the R stands for reset. And it's inverted logic, so it's a set with an overbar or a reset with an overbar. So the idea is as follows. If we want to set the latch to a value of 1, then we have to make S equal to 1, so S naught is going to be equal to 0, so we place a 0 here. And that 0 forces a 1 at the output here, and that 1 together with a 1 from the reset input will make a 0 here, and that's a stable state. So we have set the latch to an output of 1. So that corresponds to this line in here, where S is 0 or S naught is 0, R naught is 1, and the output is 1, 0. We can reverse this, and we can put a 0 at the reset input, and that will force a 1 over here, and that 1 together with the 1 that we now have here will make a 0 at the Q output. So we have this situation here where the reset is 0, and the output gets reset to a 0 at the Q output and a 1 at the Q naught output. If both of those stay at 1, so if you have this input at 1 and we have this input at 1, then whatever happens to be stored in the latch is going to stay there. So we indicate that, this is this line here, we indicate that by showing that q of t plus 1, so that's q of the next time instant, is the same as q of t, and q naught of t plus 1 is going to be the same as q naught of t. So that's the state which actually makes the memory of this element. There is a fourth state, and that is when both inputs are 0. So if this input here is 0 and this input is 0, that will force a 1 at the output here, and it will also force a 1 at the output here. So we get to a situation where both q and q naught are equal to 1, which of course is not desirable because that would not correspond to reality if q and q naught are not the same thing. We still label this as q and q naught, and we make that little star here next to that state and say this is not the desirable state. So we will actually try to avoid that state in some future developments. One thing that is desirable with this gated set reset latch is to actually have one more input which enables or disables that latch. So we can either enable or disable the latch so that the memory can either be kept by disabling the input to the latch, or the memory can be changed by enabling the input of the latch. The enabling disabling input is called clock in general, and it will actually later lead to a clock for flip-flops that the flip-flops react to for changing their state. Okay, so in this case, we have the characteristic table over here. So if the clock is 0, so if we have a 0 here, then clearly we will have a 1 at the output here and a 1 at the output here through those two NAND gates. And if you have a 1 in both of those places, we just simply keep the state in which the latch is currently sitting. So that's indicated here with qt plus 1 becoming qt, and q naught t plus 1 becoming q naught t. So we just did not change anything. The same thing happens if we actually make the clock equal to 1. So let's change this now to 1. Okay, so if the clock is set to 1, then those two NAND gates will actually pass whatever comes from the S input and invert it in the process. So if S happens to be a 1, let's take a look at that. If S happens to be a 1 and R happens to be a 0, then we would get two 1s here at this input that will create a 0 at the output here. We have a 0 at the reset input that will create a 1 here. And so now we're back to the case where we have the inverse of the set to 0, and that will create a 1 at the output here. And the 1 together with this one will create a 0 here, and so we actually set the latch. So that's the line that we have down here. Okay, and then it's not difficult to see that we could exchange the roles of set and reset and put the 0 for the set and the 1 for the reset, and then we would achieve the opposite. That would be the line that's shown in here. If both of the inputs here are 0, then both of the outputs here are 1, and we stay in the same state as we were before. That's similar to the case when the clock is set to 0. There is the fourth state in here, the one down here, that we would like to avoid in general. That's the case when we have a 1 here, and we do have a 1 here, and we have a 1 here. So now we're going to get a 0 here, we're going to get a 0 here, and that 0 in turn forces a 1 here and a 1 here, and we're back to the case where q and q naught are both at 1, and we would not like to keep that in general for a circuit like this. Here's the graphical symbol that's being used for a gated set reset latch. So the clock here is in the middle, the set in the upper, the reset in the lower part of that symbol, and then the outputs are Q and Q naught. And the characteristic table, of course, is the same for that graphical symbol as it would be for the actual schematic. One thing that is important for the analysis of memory elements and latches and flip-flops in general is to look at the timing diagram. Okay, so here is the schematic again of that gated set reset latch, and then down here are a number of waveforms shown that indicate what's happening at different times. So the time goes here along the horizontal axis. Usually the starting point is the clock, and in this particular case, a 50% duty cycle rectangular clock has been used. That could vary. There could be just short pulses going up or short pulses going down, but for the time being, we just use this particular clock signal. So now, as you remember, the clock here is basically enabling or disabling that latch. So what we will see is that in this timing diagram, only during the periods when the clock is high, anything can change at the output here. So set and reset are shown here with those two particular waveforms. So as we go now from left to right, we see that the set here turns on, and it's during the time when the clock is high, and so that will create this particular rising edge on the Q output. So it gets set. And then this continues beyond the time when the clock is on. So now the output here is frozen, starting from this point in time here. The output is going to be frozen until we reach the next part of the clock where the clock is high. Okay, and then the circuit takes a look again at what the output should be. So now set has gone to 0 in the meantime, reset has gone to 1. And so based on the fact that reset is high now and we have this edge here, we actually have the output Q go down to 0. And Q naught is just the inverse of Q in this particular case, because only one of the two, set and reset, is actually high during the clock period being high. Okay, then as we continue, there comes this little bump here, and that has no effect on the output because at this point in time the clock is low, so the latch is disabled. It continues now into the portion where the clock is high again, so that would be this area here, and in this particular case both set and reset stay low, so we keep the memory here. So keep QT. Then comes this bump here on the reset input, but it happens during a time when the clock is low, and so no change occurs. So the next interesting change actually happens here at the time when the clock goes high. It takes now a look at what currently the value is of the set and the reset inputs. So reset is low and set is high, so that leads then to a setting of the output, which means that Q goes high. Then at this point in time here, the reset goes high while the set is still high, but it's outside of the period where the latch is enabled. So we still have the clock low, so it's disabled. And then comes the point in time here when the clock goes high, and that together with the set and the reset both being high, that triggers this one to be high. In fact, that just remains high because it was high before, but it also makes this one here to go high. And in fact, as we can see here, that timing diagram needs a little bit of change here. This point here, this should go high and then continue on like this. Okay, so when both the set and the reset are high, so that would be the 1 here and the 1 here, and the clock is also high, then as we have seen previously, this makes zeros here, and those zeros make ones over here, and that makes both Q and Q naught go high. Now the interesting question is what happens when the clock goes low, thereby turning off the input. So now we will get a 0 here, and that 0 will in turn make this one into a 1 and this one into a 1. Okay, now we have to erase those from before. Okay, and so now when both of those are 1, then the latch here goes into an arbitrary state. It depends on, both of those have been 1 before, so that would make 2 zeros at the output, but not both of those can be 0 at the same time. And so the one which goes to 0 faster is going to stay at 0, and with the 0 that it inputs then makes the other one stay at high. So in this region here, okay, we actually do not know what's going to happen. It depends on very small details, like which of the two NAND gates is a little bit faster than the other, which one is a little bit hotter than the other, for example, what is actually being stored in the latch. And so that's the reason why this situation where both inputs here are at the 0, both inputs are at the 1 here, is not desirable. It's actually both inputs at the 0. It's both inputs here at the 1, then both inputs here at the 0. That leads to an unstable state. One way to get into this unstable state after the clock is being turned off is to actually make a gated D latch. Okay, where D actually stands for data. Okay, so what we do is we now do not have a separate set and reset input anymore. So those used to be the set input, this the reset input. So we actually combine them or connect them together through a NOT gate so that we cannot have set and reset happening at the same time. So now the characteristic table looks like this. If the clock is at 0, then we will get a 1 here. So if we have a 0 here, then we have a 1 here, and we have a 1 here. And that just leaves the latch in the state that it was at time t. So q of t plus 1 becomes q of t, and q naught t plus 1 becomes q naught t, irrespective of what the input at the D input is. And then if the clock goes high, so if you're making this a 1, okay, then we can actually pass the values through that we have. So if D, for example, is a 1, this is a 1, then we'll get the 0 here. And that 0 means that this will be an output of 1 here, and this will become a 0. And so we are setting the latch if D happens to be 1 at the time when the clock is also 1. And similarly, if this input here is set to a 0, okay, then we're going to get the 1 here. And if the clock is on, or the enabling is on at the same time, we're going to get the 0 here. Okay, because of the 0 here, we're going to have a 1 here. And that means that we are forcing a 1 here, and that 1 together with this one will make a 0 here. And so we have the situation where we actually are resetting the latch and storing the data value of 0. Here is the graphic symbol for a gated D latch with a D input, Q a Q naught output, and clock being the gate that enables or disables this latch. A quick look at the timing diagram. We have a clock signal again, and it is such that only when the clock is high can the output follow what the input is doing, and when the clock is low, then the current state of the latch is frozen. Okay, so we have a data signal here. So what's happening is that since this goes high during the time when the clock is high, we will get the output to react to it. Then after the end here of the clock high time, this gets frozen, and even though the D goes back to 0, it stays high until the next time when the clock is high and the gate and the latch is being enabled. Okay, now during this time, this bump that we see here is actually going to go straight through to the output. But because it goes back to 0 again before the end of that clock high period, we will actually go down to 0, and then the 0 gets stored until this point in time here. Okay, so now at this point, when the clock gets enabled again, the latch sees that the data input is high now, and so the output goes high. So that's a direct consequence of the clock having gone high. But then the data itself goes low again during this enabled period, and that will make the output go low. And then it goes high again, and the clock is still in the enabled value up until this point here, and then the contents are frozen again until we see the next clock. And so even though we have for the data a dip going down to 0 and then back to 1 again, this does not go through to the output because it's during the disabled time when the clock is low. And then comes the enabled time again. At this time, the data is high again, so that stays here at the output high, and the data is high beyond the period when the clock is enabled, and so that stays high until this point in time. And then here the data has gone to 0 in the meantime, so at that point in time we have a transition of the output going from high to low again. Now the next idea is to combine two of those gated D latches together. Okay, so here is the first one. This is called the master. And here's the second one, which is called the slave. And the key thing is that there is an inverter here between the two on the enabling input, on the clock input. So whenever the master is enabled, the slave is disabled, and vice versa. And so what's going to happen then is that the master is following the data at the time when the clock is high, and then when the clock goes low, the contents of the master are frozen, and the output from the master is then actually being transferred to the slave, because as soon as the clock here goes low and the master is disabled, then the slave gets enabled. So the slave is now taking the data from the master and passing it to the output, and the data cannot change during that time because the master is frozen. And then it repeats again. The slave then gets frozen after the clock goes high again, and then the master can follow the data again. So what this leads to is that the data transfer is actually occurring on the edge of the clock. So let's take a look at this timing diagram here. Again, we have the clock that goes high and low and high and low, and so when it's high, then the master is enabled. And when it is low, then the slave is enabled. Okay, so the data input here is going high in the middle of this period where the master is enabled, so the master is actually following what is going on here. And then at the output, at the end of this state where the master is enabled, the QM is frozen. So during this time here, it is frozen. And now, because we have the low period of the clock through the inverter, the slave is now enabled. So the QM gets transferred at this point in time into the QS. So basically that's happening here on that negative edge. We're going to have the transfer here of the value of the QM being high. Then at the point in time when the clock goes back to high, the output of the slave is now frozen. And the master can again follow what's happening at the input. So in this particular case, nothing is happening at the input, so the master actually stays at 0. And then that 0 is being transferred to the slave at the falling edge of the clock here when the slave gets enabled, because the clock is now low. So this is a transition that happens because of that clock going low there. Then we get to this point in time here where the master gets enabled again. So this bump here goes through to the master. Okay, but it is still during the time when the master is enabled that things go back to 0 again. So this never makes its way out to the slave. The slave gets enabled here and just sees this point in time here, just sees that the master output is at 0, so it keeps its output at 0. And during this time, when we are at 0 here, the master is frozen. And then when we go high again, this one is frozen again. And then during that high period here, the data happens to be high, and so the master is following that. So there is this enabling here of the clock that enables the output of the master to go high. And at the end of that period, during this point in time here, the master is again frozen. And whatever is stored in the master is now being passed on to the slave. So that's a consequence of this negative edge here. It goes back in there. And it goes back up high. Then the master gets enabled again during this period of time. So there's this dip that goes to 0. And the master is following that dip, but because during the time it is still enabled, things go back up high, the slave is never going to see that because it is frozen during this time here. Okay, so here it is frozen. So in this way, by combining two of those gated D-latches, we actually created a circuit that between its input and its output reacts to the data D, but it only reacts to the data D at the negative transition of the clock. At the transition from positive to negative, something can be passed on to the output. At all other times, it's actually not able to pass things to the output. So this is called an edge-triggered flip-flop. So here are the graphic symbols for edge-triggered D flip-flops. So the key thing here is the edge triggering rather than the level triggering. And the nice thing about edge triggering is that the edge is a very definitive point in time, whereas a level is not any particular point in time. It's a point in amplitude, but not in time. So we can have both negative edge triggered D flip-flop, like we have seen in the previous slide, or we could have a positive edge-triggered flip-flop. In a schematic, the fact that the flip-flop is edge-triggered is shown by this little triangle here at the clock input. Okay, and then whether it's positive or negative edge-triggered is shown by having either this bubble here at the input, so that would mean it's negative edge-triggered, and the absence of the bubble here indicates that it's positive edge-triggered. And looking at the characteristic diagrams here, when the clock makes a negative transition on the negative edge-triggered D flip-flop, which is indicated by an arrow that points down, then whatever value is at the D input gets transferred to the output, and to the output Q, and the inverse of it to the output Q naught. And whenever the clock is at level, either the 0 level or the 1 level, and doesn't make a transition, then no matter what the data input is, the output is just being kept at what the previous state of that D flip-flop was, of what that memory element has been storing. And for the positive edge-triggered flip-flop, everything is the same except that it reacts on the positive going edge of the clock, which is indicated by an arrow here that's pointing up. And when the clock is either at the 0 level or at the 1 level, again, the output of that D flip-flop just stays at the same level as it has been before.